Okay, so before we start, I mentioned last time about the labs. So actually, it turns out a lot of people have checked their part 1 and part 2. So there's only a few people per part that haven't done that yet. So please use this week to do that. If you, as I mentioned last time, if you really can't make it this week, because you also have to get part 3 checked off, or we should be able to accommodate some makeup next week as you're kind of, or sometime this week, but you should talk to Alberto and Philip to see what time would work for you. They'll probably try to move people into 1 or 2 slots, since we still want to have somebody in the lab while you're doing stuff. So safety reasons, etc. But I think it's not that many people that need that, so please finish that up. Okay, today what we're going to do is try to wrap up a whole bunch of topics that we talked about sort of individually to culminate toward the design of the CMOS op-amp. So we've looked at single-stage amplifiers, we looked at feedback, we looked at input, output common mode ranges, we looked at current sources, current mirrors, active loads. So all these things sort of come together when you try to design a CMOS op-amp. And so we're going to look into, then again, all these features that we talked about, offset, common mode gain, common mode rejection ratio, all in the context now of a CMOS op-amp and those topologies. But a lot of stuff should be kind of familiar already from the pieces that we've done so far. So with that, I'd like to start with sort of some of the applications for the op-amps in general and also CMOS op-amps. And the one that you've kind of started working on already in the lab, it's with bipolar transistors, just because CMOS transistors blow up much more quickly. So that's why we set the lab with bipolars. But essentially, the application is using an op-amp with external, in the external amplifier context. So what that means is that the feedback is set by external component. For example, let's say we can have something like this. It's an inverting amplifier. And, well, there will be some finite gain in that op-amp, but largely, the output voltage or the gain of this amplifier will be set by the ratio of RF to RS as long as A is large. Right. So we would say in ideal case, A would be infinity, so would have V plus be absolutely equal to A minus, V minus, and V over Vi would be exactly minus RF over RS. Right. The nice thing is here that the gain, to the large extent, does not depend at all on what's happening inside the op-amp. I could have, if A is like 10,000, I could have 10,000 or 10,100, 10,200 gain. It doesn't really matter. It will not change what the gain here is, right? And so that's kind of a nice thing about the op-amp circuits. The challenge in building this type of or op-amp is that it has to handle a whole bunch of parasitic conditions, because you just take this op-amp off the shelf, you put it on your board, you put all sorts of things around it, and there's a lot of components that you introduce unintentionally. So the op-amp has to be able to drive all these parasitic capacitances that are done externally, right? And therefore, the stability of the op-amp, since that's what we talked about last time, feedback does affect the stability. you introduce these unintentional poles, speed matters, slew rate gets compromised. So all these things that we're going to talk about later in the context of CMOS op-amps, here it's kind of unpredictable. So the challenge is to design this device so it's kind of robust to all these things that happen. Okay. A little bit easier job, and therefore more flexibility in how you can use op-amps happens with the internal amplifiers. And in that case, you're really building an amplifier somewhere on the chip, and you know exactly what the load is going to be, meaning what circuit does load that amplifier stage, what type of feedback you're tying around it. So you can relax some of these constraints and in order to be able to improve performance and kind of really push the edge on the performance or power of that amplifier. So for example, in an integrated process, I would not necessarily use the resistor because it's a very imprecise thing. If I do polysilicon resistors plus minus 10, 15, sometimes 20% is the error. So that's a pretty large error in the gain that I don't want to tolerate necessarily. So capacitors are, for example, something that is much nicer and much more well-defined in a CMOS process. So I could use something that looks like this. So let's call this delta VI. So if I apply a small signal, let's say a small, that's not DC obviously, what would be the gain of this stage? Delta VO over delta VI is like a small signal AC input, and you have AC output. Mm-hmm. Yeah. So it will be still the ratio of minus ZF over ZS, which is then minus CS over CF, right? Okay. The only slight problem with this circuit is that really there's no DC bias, right? At this input node. So an op-amp really needs some common mode, as we've seen previously, to be able to kind of bias that input transistor or a diff pair stage. So then you need to figure out some other technique or approximate technique with which you can still use this topology, but really provide a DC bias here. And what appeared as a consequence of solving this problem was switch capacitor amplifiers. And we're going to go into them just in a little bit more detail simply because of the legacy of this school and the fact that they're like probably the single most utilized topology that people have done in the last like quarter century. So a lot of people here at Berkeley, Hodges, Gray, and the others Broderson have really pioneered a lot of topologies based on these switch cap circuits and sort of made Berkeley famous in circuit area. So this is something we're going to cover real quick just so you see the utility. So let's say that instead of just static CS and CF, we have a topology where I can also use switches. So I'll use a switch here. And I'll use another switch over here. Have another switch over here. And I'll use the switches, so this is VO. These switches will be gated by control signals. I'm going to label them phi 1 and phi 2 and then draw the waveforms later. Okay. And then we have our VI. And CS. So let's say we have this type of arrangement, which essentially so has V1, Phi1 is some clock signal, some synchronization control signal, looks like this, and Phi2 looks something like this. The basic idea here is that these are non-overlapping. Okay. So there's no way that at any given point of time there will be a short, in a sense that both switches will be, Phi1 and Phi2 will be on, and so short circuit currents can go through, right? So making sure that while doing so, because of the non-overlap, I'm directing the charge to charge the capacitors the way I want. So there's no stray paths for charge to escape this system. Okay. So if we take a look at the phase where Phi1 is high, so we'll call that input sample phase. And the reason is I can redraw the circuit in that phase to be VI goes through a closed switch to CS. And then I have CF here, but notice that CF is actually connected to ground, and VO is open. So VO has there's no feedback path essentially here, because we broke this connection over here. And then there's 0 voltage across CF, so CF is in like a reset state. And all the input voltage is essentially dropped across CS. So if I then go and write the equation for charge on this node over here, so that would be, so the potential on this node is 0 because I've grounded it. So it's 0 minus VI times CS. So that's from this plate. And then I have also plus 0 times CF. That's just because the voltage across CF is 0. There's ground on both sides. So this is minus VI CS. Now in phase 2, it's called transfer. Transfer phase because now I take the charge that's on CS and I shove it into CF. And therefore, I close the loop. Therefore, I'm establishing the output voltage. And so that circuit then looks something like this. So let's see what happens at this node over here. This is Q2 is V minus minus 0 times CS plus V minus minus VO times CF. If this amplifier has really big gain, then V minus is going to be a very small voltage. And for now, we're going to assume that the gain here is infinity. So this V minus really goes to 0. Right, it's a virtual ground. Therefore, all the charge has now been moved into CF. So Q2 is now minus V0 times CF. Notice because we didn't have the overlap between the switches, in both of these cases, the charge actually remains the same on Q1 versus Q2 on this input node to the amplifier. Also because in CMOS, this input amplifier's current is 0, right? It's just hitting the gate. In bipolars, it would be hard to do this. You'd have to sort of account for some discharge of that node due to the base current, right? But so if you say that charge conservation gives you Q1 equals Q2, then you have minus VI CS equals minus VO CF. So VO over VI is CS over CF. Notice we lost the minus sign. That's simply the artifact of how we connected CS after sort of when we expelled the charge through. But the ratio is still kind of proportional to CS over CF. Now, if we take a look at a little bit more realistic scenario, the way I would really build the switches will be with, or let me do VI. And then I2 is here. This would be here. I have my amplifier. Now, in this case, it has some gain. Okay, let's call it small a, because you did that in stability. I also have some C parasitic here, and we're going to call this also VI, because it's the input to the amplifier. And then we have these switches as well. So in this case, we're just taking into account a little bit more realism in the sense that there's some parasitic input capacitance into the amplifier. Let's say that's the gate capacitance. It's also some interconnect between the capacitance and the amplifier. It's also potentially the bottom plate capacitance of this capacitor, because in MOSFET technology, the way you lay out the capacitors, you may get parasitic capacitance to substrate as well. So in this case, our Q1 is still minus VI CS, because this node gets grounded hard by this switch. But situation changes when we look at Q2. Oops, I think I'm missing. So at Q2, assuming the gain is finite, our V minus becomes VO minus VO over A, right? So VI here is minus VO over A. So then we have this situation where we've grounded the other side. So we have minus VO over A minus 0 times CS. That's the charge on CS. And then we have minus VO over A minus VO times CF. And then we also have this parasitic term of minus VO over A times CP. Right, some charge escapes into that parasitic capacitor CP. So now if you equate Q1 and Q2, what that gives you is that VO over VI is our standard CS over CF, but we have this correction term, 1 over 1 plus A, and then we have CS plus CF plus CP over CF. And we can say, okay, well, this whole thing is just 1 minus epsilon, where epsilon is some gain error, right? So if this is very small, then we can write that epsilon is 1 over 1 plus A times CF over this CS plus CF plus CP. And what we can see immediately here is kind of what we talked about. Like if A is really big, then this V minus is very small. So it basically nulls out all the effects of parasitics simply because the voltage across the parasitic capacitor is very small. Okay. But if gain is kind of moderate, then we have all sorts of issues coming from that parasitic capacitor. Also, we get the effect of offset and other things. So, if you take a look at kind of the list of limitations, we obviously have matching between CS and CF, which we said, in integrated circuits, it's better than RS and RF, but there's still a little bit of mismatch. Then large open loop gain. We'll see. So offset is non-zero. So offset will sort of play a role here because it will be the voltage that will prevent things from getting completely to virtual ground. So your parasitic capacitor will be charged with that as well. Then we have some things like switches leak, especially in modern technology. When you turn off the switch, there's actually pretty substantial current still going through it. And that will limit our conservation of charge here. Okay, so there will be it will introduce some error and make you have to go faster in charging and discharging the capacitance. So the leakage time compared to the time that you're really charging the capacitor is much smaller. And therefore, the total leaked out charge is small. Then you have things like charge injection and clock feed through. If you look at these switches, when the switch is on, we know that there's charge in the channel, right? That's the inversion that happens. And then when you're turning the switch off, all the charge in the channel squirts out, essentially both into the source and drain. And that delta Q actually ends up being dumped on CS or CF, right? And then when you're turning it on again, it kind of takes a little bit of delta Q in order to establish the channel. Right? So those little delta errors still show up as fixed error in these Q1, Q2 equations. Also, clock feed-through means that, as we know, there's some CGD capacitance here and CGS on both sides, right? So when clock goes high and low, it injects charge into this capacitor CS and CF through the switches. we can make CS and CF small because then our amplifier is faster, right? Because the dominant pole moves out. But in that case, all the parasitics of the switches injecting charge, capacitively sharing between clocks and these big capacitors essentially become more important. So there's a trade-off in kind of the bandwidth versus the error that is introduced. So a lot of these are kind of covered in 240B and 247. So for people who are more interested, I'll refer you to those classes in the future. But it's kind of a very important concept to realize because a lot of modern topologies and A to D converters, in addition to just amplifiers themselves, are based on these kinds of signal process. There's a whole class, essentially, of switch cap signal processing topologies. Okay, so, but sort of looking at this application, let's dive a little bit into that triangle that we had as an amplifier. So we're going to do just the basic two-stage. Just to be able to tie together a bunch of issues that we talked about earlier, and then we're going to move on Wednesday and Friday into higher gain topologies. But you'll see that pretty much the principles are the same. And you've sort of inadvertently looked already at some of these issues, like through some homework problems. So even without knowing it, you know how to solve these things. Well, I'll just label this VSS for now. So what we have in the op-amp, we're going to have the input stage, which is our differential pair. And then we're going to use the active load current mirror. And then from here, we're going to take this output into the second stage. And that second stage is a common source, but will be biased, loaded by another active load. Alternatively, I can also take this output and put it into an NMOS loaded with some V bias here, with a PMOS. And sometimes this topology will also be preferred just for speed reasons, because the mobility in an NMOS is better, and I want to have a larger GM in this output stage. So we'll go into those details a little bit later. But I think for now, let's just focus on kind of this part over here. And we're going to label the transistors as M1, M2, M3, M4, M5, M6, M7. We're going to analyze first just the DC conditions and gain, things like that. We're not going to show sort of where compensation is and what happens when you put this in the feedback. I can also, I can also create a flipped version of this where the input pair is P channel. And if you look in the book, that's kind of what they analyze. It's essentially equivalent. There's some noise reasons and some trade-offs for which you may want to use the P channel input, but then we have to trade off some other parameters. So we'll cover that kind of later when we get to it. But so some properties of this topology. First, the gain. So that's VO over VP minus VN. Now notice that I've labeled on purpose P on this side and N on this side, simply because the phase relationship of this input to the output is non-inverting. Right? I go pi and another pi over here, and if I go from N, I go pi, pi, and another pi, so 3 pi. So the Vn to Vo is 180 degrees, and Vp to Vo is 360, right, or 0. So therefore, this right input into M2 is non-inverting. Okay, so can somebody tell me sort of what the gain is? We've looked at M1, 2, 3, 4 topology, right, before. And we looked also at common source kind of amplifier on its own. We have 2 stages, right? One stage, so let's call it A1, and then we have A2. So A1 is this, right? And then this is A2. So what is A1 gain? That was this long derivation that we did to conclude that it's actually a very simple expression in the end. Okay, so I'm going to write it as, GM1 or 2, because those are the same, right? And then times RO2 in parallel with RO4, right? We said that, if you remember, when we looked down, we saw actually 2 RO2, right? And then when we looked up, because of that feedback, we also saw another 2 RO2 in parallel with RO4. But the current mirroring was creating this reflection of 2 RO2. So 2 RO2 in parallel with 2 RO2. So this was from 2 RO2 in parallel with 2 RO2. Right. And then there was this simplification that I did when we said, okay, if we assume that R naughts of these two are not present at the moment, so this is ground, then you can kind of look down and up just into the output impedances of the two. Okay, so that's the first one. And the second one, even simpler. We have to have a transconductance and an output impedance, right? That's how we calculate the gain of the amplifier. So what's the transconductor? GM5. And what's the output resistance? RO6 in parallel with RO5. Okay. Yeah. Okay. So yeah, that's our gain. So from the switch cap example and kind of other op-amp examples, we saw that we want this gain to be big, right? We also saw that in order for the gain to be big, since we have a trade-off between how fast GM grows versus how fast R naught grows, right? GM was the square root of current, and R naught was inverse of the current. Then we said that, okay, we really want the current to drop. So yes, your transconductance suffers, but your R naught increases much more rapidly, so your I bias is low. has to be lowered, as well as you want to boost your output impedance in order to get more gain. So in that sense, again, you kind of want your L to increase. Right. And again, both of these factors give us sort of a trade-off, right? It's gain versus speed. Because we know smaller current, transconductance drops, basically our GM over C is going to drop, so our speed is going to drop. And then with L larger, I'm also going to have a slower device. But I'm going to have more gain. Okay, so some other properties. What is the Rin of this device? Input resistance. Yeah, so we'll say infinity. Yes, there's some gate leakages in modern processes and things like that that would cause it to not be ideal. But as a first approximation, it's near ideal. R out, we sort of already covered that, right? That was this piece over here. Notice that having RO5 in parallel with RO6, that's a pretty reasonably high output resistance. So it's okay because driving on-chip caps, right? If I was driving directly the output of my op-amp, discrete op-amp component with this much resistance, it will be very hard for you to attach any capacitance and really do anything. So typically what happens is at the output stage there's some buffer, like some source follower or emitter follower that would kind of give you better output impedance. So it replicates gain, but with much smaller impedance, so you can attach a big capacitor at the output and not make that a super dominant pole. Okay. Let's take a look at some other properties. So, like output swing. Let me just repeat that stage here so we can analyze it a little bit better. So M5 is here, VO. This is VDD. This is this is VSS. This is M6. Oops. So what is the maximum output we can have? VSS minus. Notice this is maximum. Yes, there is a minimum as well. So with minimum means you're starting to hit this guy, right? So for maximum, we're worried about M5 staying in saturation, right? And for minimum, we're worried about M6 staying in saturation. So okay, so let's say one of the guesses is that VDD is VL max is VDD minus VTH5. Everybody agree with that? See some heads shaking. What is the potential here at the gate? I mean, what's this voltage drop over here? Used to write it as something like VTH plus V overdrive, right? So how high can this node go before this transistor goes into triode region? You remember the analysis of the current sources and things like that. We had something very simple for the voltage here. VOV. Yeah, that's right. So VOV, if VOV is here, then I still have VTH to come down to VTH plus VOV, right? Or VDD minus this gate source voltage. So I can climb up on VO until VDD minus the VOV. Okay, correspondingly, what is VO min? We start from VSS, okay, and then plus VOV. Okay, so that's the output. The input swing we sort of already did, so I'm just going to really quickly jot it down here so you have it for completeness. Or maybe ask you for what it is. For input, we had something like this. And this is M7. Anybody remember? For this circuit, we already sort of did these conditions. So the first condition is what? Which two transistors are critical? Is I'm changing. So I'm looking for range in VIC, right? Or let's put this as capital. Right. So I'm looking at the range in VIC. I'm moving VIC up and down and looking at how I'm squishing different transistors. Right? What happens if I start going too low? So if VIC goes low, what is VIC min? Okay, it's VSS plus VOV7 plus VTH1 plus VOV1. Right? VTH1 plus VOV1 is just the VGS on this transistor over here. Right? So both are moving at the same. So there's same current flowing through both branches, which is I bias over 2. All right. Okay, so this is the condition for M7 in SAT. What's the second transistor that's critical? I look at VIC going up. So if VIC is going up, which transistor gets squished? Well, M3 definitely gets pushed at, but can M3 really be ever taken out of saturation? Its VGD is 0, right? So it's always in saturation. You can, if you push too hard, you can if you somehow could grab this node and slam it into VDD, obviously this guy would stop conducting, right? So it would be cut off, but it won't exit saturation, as it's sort of, it won't go into triode. So it will go from saturation into cutoff, but not triode, okay? But what's the other transistor that's in the path, right? M1, right? So to keep M1 in SAT, we have to have which condition? So VIC max is how much? It starts from VDD, right? VDD minus this voltage is known, right? That's VTH 3 minus V overdrive 3. So this was VGS 3, right? So we drop down by VGS because that's a diode-connected device. And then we're at this drain. And then we go where? Up by the threshold, right? So plus VTH1. And notice here that because VTH1 is kind of has body effect because its source is not really at 0. This VTH1 will be sort of larger than VTH3, which serves us to broaden this range. So by deciding how I want to tie the body of M1, I may be able to increase my range here. Obviously, I'm kind of then compromising the gain potentially because of the body effect and things like that. Okay. Okay, so the last piece we're going to sort of touch on today a little bit is the offset. And there's two kinds. We looked at previously at the random offset pieces in differential pairs. But I'll first touch here on systematic offset. All right. Offset in general in a multi-stage configuration is something like this, that A1, because of some mismatch inside, will give you, for VID of 0, will give you some non-zero output, right? And that's going to be VOS1. And then that can plug into A2, and A2 can produce its own VOS, VOS2. Okay. For analysis purposes, we can always match that to something like this, where at the input, we have what we call input-referred offsets. So the first one will be VOS1 over A1. The second one will be VOS2, but divided by both gains. Okay? So if you're looking at how signal is really affected, it turns out, just because of this, that the offset of the second stage is always far less important than of the first stage. And you should do everything in your power in terms of transistor sizing, biasing, etc., to minimize VOS1. Right? So if you can do that, then you've kind of significantly removed the impact of the first stage offset, and second stage offset will get naturally divided by just the cumulative gain. So what we're going to try is design for VOS equals 1 equals 0, at least try to eliminate the systematic component. Right? random component we can try to kind of minimize somewhat, and we'll see you the expression for that. But and minimize VOS1 random. So that's essentially the goal, right? You maybe have to trade off some things one for another, but we'll see that in a bit. Okay, so I'll just quickly sketch sort of what happens, and then we're going to continue kind of in the next class to derive it in a little bit more detail. But what we have inherently is kind of a similar situation that was happening in current sources all along. If people remember the systematic gain error analysis with VTO, VTH, VOV going around KVL loops in current sources, well, same thing happens here. Because after all, these are active loads. Right? Okay. So we have a situation like this. M5, M6, M7. What I want to do to provide the mirroring, so I have I bias over 2, and same thing here. And I want to have, so I have I bias here, and I want to have here some K times I bias. So let's say a simple scenario. If I want to use, so I want VOS equals 0, systematic equals 0. And I'll choose K equals 1/2. So that means that I'm mirroring exactly the current that is in one of these two branches out here. Okay. So in that case, what I want to have is that W over L3 equals W over L4 equals W over L5. Okay. The reason for this is that with target current being the same in all of those, and the sizing being the same, my overdrive voltages are really all the same. So notice that if that's true, then M5 has VGS plus V overdrive, VTH plus V overdrive here, and that's